Hello, Math 1224. This is Dr. P with Lesson Launch 22.1. The more things change, the more they stay the same. So take a look at the differential equation I've written down. This is differential equation dx dt equals 2 minus x. Now I know that you're used to seeing x as the independent variable in a situation, but actually when we work with differential equations, a lot of the time we write down a differential equation in which x is a function of t. So in this situation, we're thinking if x is the dependent variable and t or time as the independent variable. And the question I want to ask is, does this differential equation have any solutions, x of t, that are constant functions? And if so, how do solutions to this differential equation behave around that constant function solution? So first, let's answer the first question. The first question is, are there any constant function solutions? Well, we could just think about this logically and say, so let's call this question 1, this question 2. There we go. So question 1, if there is a constant function or a constant solution, let's call it x of t equals c, capital C, then we could just think about what that would mean in terms of this differential equation here. Well, that would mean that dx dt is 0 because x of t is a constant function, and that thing's derivative is 0, and that would have to be equal to 2 minus x of t. X of t is just c, so c would have to be equal to 2. So now let's investigate that solution, that possible solution, x of t equals 2. So if x of t is 2, the constant function 2, then if I just want to check that that's actually a solution to my differential equation here. So if I substitute that into the differential equation, I get dx dt is indeed 0, and 2 minus x is always equal to 2 minus 2, which is 0, so that checks out. So this is a solution. Now, is it the only solution to that differential equation? Probably not. Almost surely not. But it looks like this would be the only constant function solution, because any constant function solution, as we said, would have to have a 0 here, which means this would have to be 0. And that forces, if x is going to be a constant, that forces that constant to be 2. So what we have here is a solution to this differential equation that is a constant function. And when that happens, what we do is we call that something special. So we call this is called an equilibrium solution. So here's why. If x were some quantity that changed with time, and x was governed by this rate law here, the rate of change of x with respect to time is 2 minus the value of the quantity, then that would mean that if x somehow started out at having value 2, then it would never change, because its rate of change would be, by definition, equal to 0. So that means that if the value of this quantity is 2, it's always going to be 2. That makes 2 an equilibrium point. Now, one interesting question to ask is, what if x wasn't 2? What if x, for example, started out somewhere near 2? How would x behave in that situation? So there are a couple of ways of analyzing that. One I'm going to do in this video. I'm just going to use a very crude version of Euler's method. And then I'm also, in the next video, going to use a slope field to analyze this question, and probably do one more example. But first, let's use Euler's method here. All right, so we're going to move over here. We're going to ask ourselves, let's see, so we're going to use Euler's method to analyze the behavior of a solution if x of 0, we're just going to pick on this particular value. Good Lord, my penmanship not very good today. X of 0 is a bit different from 2. All right, so again, I'm just going to remind myself here, my differential equation is dx dt equals 2 minus x, and that's going to govern how x is going to behave. So let's create a table of values. and then I'm going to put t here, and I'm just going to plot out some values of t. Now, by the way, Euler's method, you can also go backwards from the point where you're starting. There's no reason you have to go forwards, but I tend to go forwards because I find it a little bit more intuitive most of the time. But I think one of the homework problems asks you to go backwards in time. Okay, so time's going to march forwards, and I'm going to make my step size 1/2 because I want to do a better job of illustrating how this method works if the step size is not a whole number, because I think you'll have good rate of change reasoning for whole numbers, but maybe could use a little practice with non-whole numbers. Okay, so I'm just going to write down for each value of t on this table the values of x and dx dt. Okay, so for x of 0, I'm going to pick some value of x that is a little bit bigger than 2. So let's pick x of 0 equals 2.1, and we're going to see if we can construct a solution using that initial value. Okay, so x of 0 is 2.1. Okay, and then according to this differential equation here, we're going to use this frequently now. That means that my rate of change has to be 2 minus 2.1. So that means my rate of change is negative 0.1. All right. Now, if I take this over a interval of length 1/2 over a dt of, or delta t of 0.5, this gives us delta x equals, that's going to be 1/2 of this amount here because I'm marching forward 1/2 of a second. So my delta x is going to be 1/2 of negative 0.1, that's negative 0.05. Okay, so that means that this value between 0 and 0.5, x is going to change by negative 0.05. That's going to take me down to 2.05. All right, well, if x at 0.5 is 2.05, then that means that my rate of change is 2 minus that, which is negative 0.05. Okay, and then if I take that over an interval of length 1/2, then that means this value, x, is going to change by half of this. So this is going to drop by negative 0.025. And now my poor planning comes into play here because there's no way I'm going to get all this in that little space. So let me just, I wish there was some easier way of erasing things and explain everything, but explain everything is just not that hospitable when it comes to doing that. Anyway, this should give us a good enough idea anyway. Sorry about that. So anyway, x of 1 should be 2.025, and then that makes this next rate of change here, dx dt at t equals 1, negative 0.025. Okay, and you're probably starting to get the idea. If that's the rate of change, then over another interval of length 1/2, from 1 to 1.5, this amount is going to change by half of this. So that's going to make x of 1.5 equal to 2.0125. Anyway, I'm just going to fill in the rest of this because I think you probably got the idea. If not, then there's something I needed to explain earlier in the process, probably. Okay, anyway, these numbers are kind of ugly. And by the way, one thing I want to point out here, these are not exact values. In fact, let me write that down. These are not exact values for this solution. There is a solution having this initial condition, x of 0 equals 2.1. There is a solution there, but it's not exactly this. This is only an approximation for a solution, and that again is because when I do Euler's method, I'm acting as if this is going to be the constant rate of change between 0 and 0.5, between t equals 0 and t equals 0.5. And that rate of change is not going to be constant. If I have a negative rate of change, this is going to decrease continuously, and as this decreases continuously, the rate of change is going to it's going to increase. In terms of magnitude, it's going to get slower. Okay, so I'm fudging a little bit here, but one thing that is discernible from this little experiment here is that as time increases, as time progresses, this solution here, it's getting closer to 2. Remember, that 2 was our equilibrium. So if I nudge x a little bit off of 2, off of that equilibrium, x is sort of going to wander back towards it, at least if x is a little bit greater than 2. Now, I could have also done this experiment with a value of x less than 2. Let's just start out. I'm not going to do the calculation in quite the same level of detail, but I want to show what would happen if x were a little bit less than 2. And in fact, let's nudge it a little bit further this time. Let's just say x is, there we go. Let's say x is 1 when t is 0. So quite a bit less than 2. All right. You can tell I'm kind of tired of dealing with all the decimals here. So again, differential equation is dx dt equals 2 minus x. So if my rate of change is 2 minus x, then my rate of change here is 2 minus 1, which is 1. And then let's again take step size of 1/2. I could have picked a different step size, no problem. Okay, well now my rate of change is 1. So if I take that over an interval of length 1/2, then that means that my change in x is going to be 1/2 times this rate of change here, which is 1. So 1 plus 1/2 of 1, sorry, I need to point out which 1 I'm talking about. So my x of 0.5 is going to be 1 plus 1/2 of 1. That's what that is, okay? That's going to give me 1.5. And then that means that my rate of change there is going to be 2 minus 1.5, which is 0.5, which means my change over the next interval is going to be half of this, which is 0.25. So now x of 1 is going to be 1.75. So my rate of change then is going to be 0.25. And again, you're noticing this phenomenon that x sort of gradually marches back towards the equilibrium. Isn't that neat? Okay. Now, it's possible we could have just, I wanted to illustrate the use of Euler's method here because I feel we didn't get quite enough practice doing this in the abstract. We did it with rabbits in class, but I'm not sure that that really conveys the total idea of how to do Euler's method. But anyway, we didn't have to do all of that work to see what happens to non-equilibrium solutions. We could have just sort of glanced at this and then think really hard for a minute about what happens, all right? If x is, let me write this down. I'm just going to write down some observations here. If x is greater than 2, what does that mean about dx dt? Then dx dt is going to be 2 minus something greater than 2. That means dx dt is less than 0. So x decreases over time. That's if x is greater than 2. So as long as x is greater than 2, it's going to decrease towards the equilibrium. And then if x is less than 2, then dx dt is going to be 2 minus something that is less than 2. That's going to make that greater than 0. So x is going to increase towards the equilibrium. And what's actually going to happen is in any non-equilibrium solution, x is never going to quite hit the equilibrium. If it did, it would just stay constant at 2 forever. But non-equilibrium solutions never actually meet the equilibrium solution. And that's because solution curves of a differential equation don't actually meet one another. Okay, anyway, that's enough for that video. In the next video, we'll talk about how to analyze all of this graphically and see it actually playing out in the coordinate plane. So stay tuned.